In the last video, we talked quite a bit about recursion, and in this video, we're going to finally cash out recursion and give a theoretical account of how one can do computations on the natural numbers. So what we're going to do in this video is something pretty exciting. Is we're going to set up arithmetic on the natural numbers. Just to briefly go over the recursion theorem one more time, what we said the recursion theorem is saying is that we have some set A, we select some starting element, little a, within A, and we have some function, big F, which is going to deal with the members of A and take them to set A. And what we said is that there's this other function, little h, it exists and it's unique, and what it's going to do is it's going to take the natural numbers to the set A, and it's going to be set up in the following manner. We're going to let h of 0 be equal to little a that we selected from the set A, and we have this relation that h of n plus is equal to f of h of n. And I didn't give a proof of this in the last video, but just to remind you what the intuition is, why it is that this function is unique, and it's completely determined by all of the starting conditions, is that once we let h of 0 be equal to a, we can start to build a table for h. In other words, we can start to compute with h. So we know that h of 1, by this relation, is equal to f of h of 0, which is equal to f of a. And then we just continue. H of 2 is equal to f of h of 1. We know h of 1 is, so h of 2 is equal to f of a. And then we just continue. H of 3 is going to be 3 applications of f to a, and h of m is going to be m applications of f to a. So hopefully you can see from this that once I know what h of 0 is, once I define h of 0 to be something, and I set up h and f to be related in this manner through the succession, and I know what f is doing, then h is completely determined. And in my terminology, I say that the table of h is completely determined. One additional thing to note here is that this function taking a to a is left in the abstract, and a is left in the abstract, so a can be any set. And in fact, when we set up arithmetic, we're going to let a be the set omega, so f is going to actually take omega to omega, and h would also take omega to omega. So having done the preliminary work on recursion, we're going to now set up addition. And the way we're going to do that is by writing formulas of the form h of 0 being equal to some starting element a, and preserve this recursive relation that h of n plus is equal to some f of h of n. So what we're going to do first is just set up the addition of 2 to some element in omega. So we're going to set up the function which is going to add 2 to a number. So this is going to be a function from omega to omega. So to set up this function in this manner, we need to select a little a, that starting element, and we need to select some f. So what we're going to do is let a2 of 0 just be equal to 2. So we want that starting element, that h of 0, to be equal to 2. Because when we add 2 to 0, we want 2 out of that. So we're going to set up that as a first formula. And now we need to select what f is. What kind of thing f is going to do to h of n. So we have the second formula, a2 of n plus, being equal to some function on a2 of n. And the function we're going to select, that f is going to be the successor function. So we're going to say that a2 of n plus is equal to the successor of a2 of n. And it turns out that these two formulas are sufficient to set up what it means to add 2 to a natural number. And just as a reminder, the action of this plus is just it's a successor function, but we're going to let it be the big F function, which is going to take omega to omega. And it's just a successor function as we're used to. So I claim that these two formulas here and here are completely sufficient to set up what it means to add 2 to a number. So to see the intuition behind that, let's build the table now for a2. So we start with this, that a2 of 0 is equal to 2. That's just because we want 2 plus 0 to be equal to 2. So now we have a2 of 1, which we're going to interpret as 2 plus 1. So by the recursive relation, a2 of 1 is going to be the successor of a2 of 0. We know what a2 of 0 is, it's 2. So this is going to be the successor of 2, which is 3. So that captures the idea that 2 plus 1 is 3. And then we just continue in that recursive manner. a2 of 2 is going to be the successor of a2 of 1. We know what that is already, that's 3. So that's going to be equal to the successor of 3, which is 4. So that captures the idea that 2 plus 2 is 4. And we just continue building up the table. So now a2 of 3, by the same line of reasoning, it's going to be 5. So hopefully you can see here that these two formulas are going to completely determine the table for a2. It's going to completely set up what it means to add 2 to a natural number. From the recursion theorem, we've now set up what it means to add 2. We've defined the function. We know from the recursion theorem that it's unique, it exists. So we've done that for adding 2. How about for adding m, just adding some natural number m? So we're going to continue in the same manner. We're going to say that a sub m of 0 is going to be equal to m. So we define it in this way because we want to capture that idea that m plus 0 is equal to m. And then we continue with pretty much the same formula as before we had for a2. So a sub m of n plus is going to be equal to the successor of a sub m of n. So now we're going to do what we did before. We're going to build a table for a sub m. So we start here from that first definition there. So a sub m of 0 is equal to m. We calculate a sub m of 1. So that's going to be the successor of this. And we know that's equal to m. So a sub m of 1 is going to be equal to m plus. And this makes sense so far because we want m plus 1 to be equal to m plus, the successor of m, the number right after m. And then we set up m plus 2, or a sub m of 2, to be equal to the successor of m plus, or m plus plus. So hopefully you can see how when we continue in this manner, we can also set up what it means to add m to a number. Not just 2 to a number or 3 to a number. We can generate this whole collection of functions m, which is going to set up what it means to add m to a natural number. We could keep using that terminology using the a sub m sorts of functions, that collection of functions which is going to describe what it means to add m to a number. But eventually we want to describe that notation in terms of the comfortable notation that we're used to using, like when we see 2 plus 2. We want to interpret that in terms of the a sub m collection of functions. So we're going to revert to the comfortable notation using plus in the following manner. We're going to define that plus symbol as a function which takes some ordered pair in the Cartesian product omega times omega. For example, that ordered pair might be 3, 4, the ordered pair 3, 4, and it's going to output it to a number in omega. So being a function, it's going to be a list of ordered pairs such that it has the following definition. The plus sign is going to be equal to the set of ordered pairs where the first component, that ordered pair, which is itself an ordered pair, mn, is a member of omega times omega. The second component of the bigger ordered pair, p, is going to be given by the following. P is going to be a sub m of n. And hopefully this makes sense because let's say I input the ordered pair 2, 3. So let's say I start with the statement 2 plus 3. So I'm going to interpret this functionally as the input, the ordered pair input 2, 3 being fed into the plus function. So I have m equals 2 and n equals 3. So to get my p is going to be equal to a sub 2 of 3. So interpreting it functionally, p is going to be equal, the output of this thing is going to be equal to a sub 2 of 3, which we've completely set this up recursively. This has a recursive definition, so this is going to be justified as being equal to 5. So of course you can write these sorts of functional statements as this, a plus, taking in the ordered pair input, like that, but we're just going to call this thing m plus n. So whenever you see m plus n, you could also interpret it as the plus function taking in as its input the ordered pair m and n, and outputting the value of whatever m plus n is. So the motivation for going back to the comfortable notation is that once we define up the plus function, the addition function, as this, we could take the a sub m's as definitional. So we can set up what the a sub m's mean, and then we can say that the following two propositions are theorems. So we can say that m plus 0 is equal to m, and also that m plus the successor of n is equal to the successor of m plus n. And those are pretty easy proofs, just because they follow from the definition of A sub m. So one nice thing about building up this collection of theorems is that we can begin to prove the expected properties of addition, such as the commutative property, that m plus n is equal to n plus m, the associative property, that doing m plus n first and then adding that to p is the same as having m and then adding that to the quantity n plus p. So I leave a lot of these proofs as exercises just because there are a lot of interesting proofs. But one, or actually two prerequisite proofs you'll need to do to prove the commutative property, I'll actually go through in the next slides. Here's the first theorem you'll need to eventually prove the commutative property. And the theorem is pretty intuitive. So we know already that m plus 0 is equal to m, but now we're going to prove that 0 plus m is equal to m. And notice that these two statements are a little bit different. So what this statement is really saying is that it doesn't matter what m I feed into the a0 function, it's always going to give me the input. In other words, 0 is acting as an identity. So it's saying that a0 of 0 is going to be 0, a0 of 1 is going to be 1, a0 of 2 is going to be 2, and then so on. That a0 of m is going to be m. So we're making this claim about all the values of the a0 function. So this is the sort of claim we're going to have to prove by induction. So the proof is going to be as follows. We're going to set up the set T. It's going to be all the natural numbers that have this following property, that 0 plus n is equal to n. So it's pretty obvious that 0 is in the set T, because we know that 0 plus 0 is equal to 0. Anything plus 0 is 0, so 0 plus 0 is 0, and then 0 is equal to 0, so 0 is in the set T. Let's suppose that k is in the set T. We're going to now show that k plus is in T. So we're going to calculate with 0 plus k plus and show that's equal to k plus. So 0 plus k plus, I'm going to use that theorem of addition, that a function, addition function plus its successor is going to be the successor of 0 plus k in this case. So that was one of the two theorems we had, that this line implies this line. So now I'm going to use the inductive step. So I know k is in T. So I know that 0 plus k is equal to k. So I have 0 plus k here. I'm just going to make that substitution. And then I just have k plus equals k plus. So that shows if k is in T, then k plus is also in T. And therefore the set T is equal to all of omega. So that proves the statement that 0 plus m is equal to m for all natural numbers m. So that's the first theorem you'll need to prove the commutative property. And the second theorem is going to be this, that for any arbitrary m in omega, and for all n's in omega, m plus n is equal to the successor of m plus n. And notice how this is a little bit different from the other theorem we had, which was that m plus n plus is equal to this right-hand side. So now we're showing that m plus n is equal to this right-hand side. And it seems intuitive, because the equivalent statement is as follows. The successor of m, which is m plus 1, added to n, is equal to m plus n, and then take the successor. So we know that intuitively, yeah, this thing is going to be true. But let's give a proof. And again, we're going to do this by induction. So we're going to take m as a fixed number in omega. It's going to be some arbitrary number in omega, and we're going to induct over n. So I'm going to form the set T, so it's going to be all the n's, such that n is a natural number, and that m plus n is equal to the successor of m plus n, the property that I'm trying to show. So let's first show that 0 is in T. So I make the substitution, and I'm going to show that this statement is going to be true for n equals 0. So m plus 0 is equal to the successor of m plus 0. And then this is pretty easy. I know that anything plus 0 is equal to that first thing, so m plus, and same argument, m plus 0 is equal to m, and then I have the plus there, so that's equal to m plus. So 0 is obviously in T. So let's now show the inductive step, that if k plus is in T, then k plus is in T. So now I have m plus k plus is equal to m plus k plus, and then plus one more time. So I'm trying to show that k plus is in T. So again, I'm trying to show that this statement holds for k plus. So what I'm going to do first, I'm going to deal with this left-hand side. I see that something added to the successor is going to be that something plus k, and then take the successor. That was that second theorem that we had when we subbed the meaning of plus. So I have that. And by the same argument, m plus k plus is going to be equal to m plus k, and then add another plus outside. Okay? Since k is in t, going back up here, I know that m plus k is equal to m plus k all plus. So I'm going to use that in the substitution right here. So m plus k is equal to m plus k with a plus, another plus on the outside. So now I have two pluses on the outside. And I just see that the left and right hand sides are equal. So if k is in t, then k plus is also in t. So t is equal to omega, and that completes the proof. So that concludes our definition of addition. And I'll leave it to you to prove the other interesting properties of addition, like commutativity, associativity. And what I'm going to do now is set up multiplication. So just like we are considering a class of functions a sub m, we're going to let this class of functions m sub m be a collection of multiplication functions. And these are going to take, again, omega into omega, and the plus is going to have its usual meaning as a successor. So I'm going to continue in that recursive manner. I'm going to say that m sub m, where m is any number, any natural number of 0, is going to be equal to 0, because I want to capture the property that m times 0 is equal to 0. And then I'm going to set up this other recursive definition that m sub m of n plus is going to be some function f on m sub m of n. And again, I have that question of what should this f be? And perhaps as a challenge, you might want to pause the video and see if you can come up with your own definition of big F. And also remember that we've defined up addition, so you're allowed to use addition as well. So if you want to pause the video and give it a try. Alright, so we have big M of 0 is equal to 0. And here's how we're going to define m sub m of n plus. It's going to be equal to m sub m of n, and we're just going to add m, whatever that subscript is there. We're just going to add on m again. So hopefully this makes sense, because when we have m times n plus, we have n copies of m, so that's captured in this first term, and then we have one more copy of m to include there, because we have the successor of n. Alright, so this is going to be the definition for multiplication by m. And again, this makes sense because we know what this symbol means. We've already defined addition. So now we can start to define multiplication in terms of addition. So let's now prove that the computations are going to make sense. So let's calculate with one particular multiplication function, m sub 3. So this is going to be a function which is going to multiply a natural number by 3. So we're going to define m3 of 0 being equal to 0, and m3 of n plus being equal to m3 of n plus 3. Alright, so now let's build a table for m3, the multiplication table for m3. So m3 of 0, which we're going to interpret as 3 times 0, is going to be equal to 0. m3 of 1 is going to be equal to m3 of 0. We know what that is, that's 0. So that's equal to 0 plus 3, which is equal to 3. And m3 of 2 is going to be equal to m3 of 1 plus 3, which is 3 plus 3, which is 6. And then continuing, m3 of 3 is equal to 6 plus 3. So you can see we're taking the previous number, just adding 3. That's going to be 9. So you can see that this sort of computation is going to make sense. And just like we did for addition, we dealt with that class of addition functions, and then we reverted to the plus notation. What we're going to do here is we're going to say that having dealt with the multiplication functions, we're going to revert to the comfortable notation with the times sign, the dot symbol. So we're going to say that this dot symbol is equal to a set of ordered pairs. And again, it's going to be a function from omega times omega. So its input is going to be an ordered pair, and it's going to output some natural number. So the m and n are an omega, and then that output p is going to be given by the following. It's going to be the particular multiplication function, m, which is going to be given by the first ordinate in the ordered pair m sub m of n. So again, let's say we have something like 2 times 4. We could interpret that as feeding the ordered pair 2, 4 into the times function. So the input's going to be 2, 4. Then p is going to be given by m sub 2 of 4. So the particular multiplication function, in this case 2, is going to operate upon 4 to produce the output, which is obviously 8. So now if we set up the definition as such, we now have the theorems. M times 0 is equal to 0, and these are justified in the same way as the addition ones were. So m times 0 is 0, firstly. And then secondly, m times the successor of n is equal to m times n plus m. At this point, we've set up the tools for multiplication in order to prove this interesting theorem, that if I have two natural numbers, m and n, that if I know that m times n is equal to 0, then m is equal to 0, or n is equal to 0. And of course, this is an important theorem for doing things like factoring and solving polynomial equations. So the theorem is that, what I just said, m times n being equal to 0 implies that m is 0 or n is 0, or both. So the way I'm going to prove this is by contradiction. I'm going to suppose that m times n is 0, and that m is not equal to 0, and n is not equal to 0. So I'm going to assume these two propositions, which I'm going to show lead to contradiction. So if these two are true, that m is not equal to 0 and n is not equal to 0, then I must be able to write m as the successor of something else. Let's call it a. So m is going to be equal to a plus, and same thing for n. Is if n is not 0, I can write that as b plus for some a and b in the natural numbers. So now I'm just going to do the computation. So if m times n is equal to 0, then a plus times b plus should be equal to 0. So now I just apply a definition for multiplication. I have the theorem that a plus times b plus is going to be a plus times b plus a plus. That's going to be equal to 0. And then finally, I have that theorem for addition, that when I have something here and I add it to the successor, that's going to be, in this case, it's going to be equal to the successor of a plus times b plus a. And notice that this statement here is a contradiction because what I've shown is that by taking the successor of something, I can get to 0. And I know that 0 is not the successor of any natural number. So this is the contradictory step here. And since I've shown that these assumptions lead to contradiction, I conclude the negation of m is not equal to 0 and n is not equal to 0. So the negation of this is true. And the negation of this is equal to m is equal to 0 or n is equal to 0. So that concludes the proof. At this point, we have the tools to prove all the common theorems that we want to prove, like commutativity, associativity, distributivity, and other identities, like additive identities, multiplicative identities. And a lot of those are going to be left as exercises for you guys. And the last thing I'm going to do is define up exponentiation. So we're going to do this in a very similar way. We're going to consider the class of functions, the exponentiation functions e sub m, where m is like the base here. And we're going to define up exponentiation recursively. So we're going to say first that e sub m, where m is some natural number, of 0 is equal to 1. And this is going to capture that property that m to the 0 is equal to 1. Furthermore, for that recursive definition, e sub m of n plus is going to be equal to m times, again, we've defined up multiplication, so we know what this symbol means, that m times e sub m of n. And hopefully you can work out for yourself why this second formula makes sense. And one thing I'd like to point out too is notice the symmetry of this formula, the recursive formula for exponentiation, with the recursive formula for multiplication, in the sense that in our chain of reasoning, we first defined up addition, we used addition to define up multiplication, then used multiplication to define exponentiation. So you can think of these operations as being in a hierarchy, where multiplication is the next highest operator after addition, and exponentiation is the next highest operator after multiplication. And you can see that when defining the formula for the next operator in the recursive step, you're using the next lowest operator. So when we defined up exponentiation, we used multiplication. when we defined multiplication, we used addition. And then when we defined addition, we used the notion of successor. So hopefully you can see the symmetry between this formula and this formula in terms of their shape, their morphology. And indeed, you can continue beyond exponentiation to define up the next highest operator. So that the recursive step, when you define that operator, is going to involve exponentiation. And the next hyperoperator, and that's a term that's often used, the hyperoperator after exponentiation is called tetration. And it's called tetration because the prefix tetra means fourth. So this is going to be like the fourth operator. Exponentiation is like the third operator. And you can even continue beyond tetration. You continue to pentation, the fifth hyperoperator, or hexation, the sixth hyperoperator. I certainly encourage you to play around with those hyperoperators. It's a good deal of fun, especially if you're computationally oriented. And you can really see how large numbers really start to get. And just as a representative example, in the second practice problem, I give you a computational example where you can see how large these numbers get and how quickly they get once you start dealing with these hyperoperators. So that concludes this video. As always, thanks for watching. Feel free to subscribe, stay tuned for more videos, and if you enjoyed the video, give it a thumbs up. And thanks for watching.